Okay, so welcome all to another session of GATE classes from NPTL. So, for the last few weeks, we have been following CRE, Chemical Reaction Engineering. But before that, just checking in, am I audible and if is the screen visible to all? Can someone just? Okay, fine, good. Okay. So yeah, as I said, we were following chemical reaction engineering for the last few weeks, probably like some 6 or 7 weeks, and we were mostly focusing on chemical reaction engineering one, or CRE one, which basically includes reaction kinetics. So in reaction kinetics, we looked at rate of reactions, various kinds of reactions, first order reaction, second order reaction, and so on. And we we also looked into how some peculiar cases, for example, autocatalytic reactions, reversible reactions, and so on. And after reaction kinetics, we looked into ideal reactors. So basically, ideal reactors are of three: batch, PFR, and CSTR. We looked into how each of these three reactors work, and how to arrive at their design equations, and we solved a lot of problems based on the design equations of these ideal reactors. And after that, we looked into some more topics such as multiple reactions. So multiple reactions are basically series and parallel, and we looked at how we can arrive at the equations for multiple reaction series and parallel reactions. We looked at something called as optimum time for a series reaction. Then we looked at how we can decide, or how the temperature of a reaction can be decided based on the activation energies and so on for parallel reactions, and so and so topics. So that that was about the major topics in CRE 1. Now CRE 2, there are mainly a few topics. So the first topic is non-ideal reactors, and then comes catalysis. So you know in catalysis itself, there are various topics. We'll be covering all those in the coming few weeks. But anyways, as I said, um, we'll uh, we'll start with CRE2 from this class. We'll briefly look into non-ideal reactors, and we'll try to solve some previous year gate problems as well, just like how we have done for the past few classes. So we'll first look into some basic concepts, just brief through them, very quickly, with regards to non-ideal reactors, and then we'll look into some previous year gate questions with regards to non-ideal reactors. Fine. So yeah, let's go. So we did learn quite a few things about ideal reactors. So let us take CSTR, for example. So I'm pretty sure all of you must be able to recollect the design equations or the peculiarities of a CSTR. So CSTR is also known as a mixed flow reactor. So like one of the assumptions, one of the most major assumptions in CSTR is that once the feedstock enters, once the feed enters, it is completely mixed, right? So let's say we are having a reaction, a very simple reaction, let's say A giving B. And if Ca0 is the initial concentration of A that enters the CSTR and Ca is the outlet concentration, this assumption says that, you know, the concentration of A inside this reactor is also Ca. Okay. So that is one of the major assumptions of CSTR. But this is an ideal case. In real cases, what happens is, some amount of A can get stagnated here like this, or in, let's say, in both these corners, A gets stagnated. Now let's say this is Vs, and this is also Vs. Like Vs is the volume of the reactor that is occupied by the this stagnant reactor. So now what happens is, the whole reactor volume is not available for reaction. So that means there is obviously a decrease in your conversion or your efficiency of the reaction. So this is one case. Another case, what we can say is, again, we'll just use the example of CSTR itself. There is something called as bypass. So let's say this is a molecule of reactant A. Instead of going to this reaction system and getting reacted and staying inside the reaction system for a time t, what can happen is this molecule of A can just bypass this whole thing, and without getting totally converted, it can just get out. That is also a possibility. So this is something called as bypass, and this is stagnation. So there are various cases in real situations where your total volume of the reactor is not available for the reaction, or there are some peculiar cases where all of your reactants are not able to perform the reaction properly. So this is where non-ideality occurs. So these are some basic examples of how non-ideality occurs in a reaction. So it could be stagnation, it could be bypass, it could be a lot of other things. And yeah, so non-ideality, by the name itself, it's just a deviation from ideal case. So yeah, so that is where this whole concept of non-ideal reactors and non-ideality, occurs. So some of the reasons for non-ideality can be, dead zone or stagnation. Then something called as this bypass, or you can even say it as channeling. And other thing is turbulence. Now this turbulence, this is very important when we are dealing with PFRs or plug flow reactors. So one of the basic assumptions of a plug flow reactor was that the flow is laminar, right? The flow is laminar and the fluid is ideal. So that is a very important assumption in plug flow reactors. And if there is turbulence inside the system, then the system again deviates from an ideal plug flow system. So yeah, so these are some of the causes of non-ideality in reactors. So to account for non-ideality, we use something called as residence time distribution, or you can even call it as RTD. So a residence time is basically, okay, let's take a case of PFR. So this is the entry point of the PFR and this is the exit point of the PFR. And let's say we have 5 molecules of A that is just entering this reactor. Now, by ideal case or ideal PFR, all these reactors that enters at the same time will exit at the same time. Okay, that is one of the ideal, uh, you know, ideal PFR assumption. So all these molecules of A will exit at the same time. Now, as I said, in non-ideal reactors, this is not the case. So if we take a non-ideal PFR, and if we take the same scenario, let's take five molecules of our reactant A at entry and exit. What happens is this will take one time, this will take a different time, this will take a different time, this will take a different time. So each molecules can take different time and different routes to get from your entry to the exit. So that is what is accounted by residence time distribution or RTD, right? So one term that we need to address here is residence time. So residence time is basically the time spent by the reactant inside the reactor. So this is simply put what you mean by residence time. And the distribution of this residence time for different molecules is what is known as residence time distribution. So residence time distribution is the distribution of residence times. Now, how we find this residence time distribution? We use something called as a tracer. So tracer is basically an inert substance which can have some sort of color or some sort of detection mechanism, and it is inert in nature, and it is usually very soluble in your reactant system, which is usually water. So you must have done some experiments if you have done CRE lab in your course. So you must have done some experiments where you inject some sort of color inside your reactor, which is basically just water running through the reactor, and you would have to calculate the time and find the residence time distribution and so on. So you some of you must have done it in your CRE lab. So yeah, so that is what we call as tracer. So we inject this tracer inside our system, and we use the exit time of the tracer to find the residence time distribution. And you know you can inject the tracer in two ways. So one way is called pulse tracer, or which is basically injecting a significant amount of tracer in just one shot basically. And then there is something called as step tracer. So step tracer, it's basically like you are injecting let's say a unit amount of tracer at equal intervals of times. For example, it will go something like a step. So at each time you will be injecting a tracer. So this is a one shot injection mechanism, and this is a sort of continuous injection. Okay, so fine. Let's take a PFR, and let's say we are injecting this PFR with a tracer of, let's say, M amount. This is our tracer, and let's say we have a flow rate nu inside the system, and let's say we are having an outlet concentration C at a time T. Then so basically M is your tracer, Nu is your volumetric flow rate. C is your concentration of tracer. Yeah, C is the concentration of tracer. Okay, not your reactant or product. So C is the concentration of tracer in your output at an interval time t. So what we can do is we can plot a graph with this tracer system. So if we plot a graph between the concentration of tracer in your output C and time t, we'll get a graph. We'll have two graphs. So let's take one graph at the input and one graph at the output. So let's say we are injecting this PFR with a pulse tracer, and we are recording the concentration at time t in the output. So as I said, a pulse tracer is basically injecting one single shot of your tracer at a single go. So let's say we are injecting our tracer at time, let's say t0. So your input curve will be a straight line like this, or sometimes you can refer this using your delta or delta Dirac functions and so on. So this arrow mark means this is having a very high height, I would say, but the thickness of this impulse or this curve is very low, and it is such that the area of this is 1. So that means it will go on like this. The height of the impulse will be infinitely large, but then your thickness of that uh, curve or the impulse curve will be very low, and the curve is in such a way that the area under this curve, which is basically uh, the area under the curve C versus T, that will be 1. So this will be your plot of concentration versus time at input. So we are having an input of this pulse tracer and time t0, and we get an input curve like this. The output will be something of this sort. And here also, you know, fine, let this be. So let's say we have an output like this. Now the resonance time E can be calculated as C, the concentration of tracer at the output, by integral of 0 to infinity C dt. Or basically, this is the concentration of the tracer at time t divided by area under C versus T plot. And we can even have a formula like this, which is C nu by M. So this is your residence time at a given time t. So now let's say if you are plotting or if you are finding your residence time E for different times from 0, T0, T1, T2, and so on up to, let's say Tn, we can plot something called as your residence time distribution or E curve. So this E curve is basically your curve between E and time T. And this will also will become something like this. This is at your output, okay? And the area under E curve will be equal to 1, right? Or you can, All right. Or you can write this as integral of 0 to infinity e dt is equal to 1, which is basically your area under E curve. Okay. So a lot of the problems or questions with regards to non-ideality or non-ideal reactors or residence time distribution will be using this concept basically, such that the area under your E curve is basically 1, right? So yeah. So also one more thing that we need to note, that this area under the E curve represents the fraction of material leaving the reactor. Okay, so if we have an E curve like this, let's say the E curve starts from 0 and ends at time t, this area will be the fraction of the material leaving the reactor at time t, right? So that is the significance of this area under the E curve. So again, area under the E curve represents the fraction of materials that is leaving the reactor within a time t, right? Okay. So using this data or the residence time distribution, we can have, uh, you know, these are called as moments of RTD. So there are basically three moments of RTD. So what are these moments? The first one will be, mean residence time. Mean residence time, in you can even vaguely term it as average residence time, and it is usually represented as T bar, and this will be equal to integral 0 to infinity t e of t dt. So this is your first moment, mean residence time. You can even, expand this, because e of t is basically c by integral of 0 to infinity c dt, right? So you can apply this expansion here, and you can write your mean residence time as integral of 0 to infinity t c of t dt by integral 0 to infinity c dt. So this is your first moment, which is mean residence time, or which you can also vaguely term it as, average residence time of the reactor. Or, this is basically the average residence time spent by the molecules inside the reactor. All right. The second moment is the variance. So variance is basically integral 0 to infinity t minus t bar, and t bar is the mean residence time. So t minus t bar the whole square e of t dt. And this variance basically represents how spread your distribution is, or spread of your RT distribution. Okay, and then there is one more moment, which is called as skewness. So skewness, which is represented as s cube, and that will be 1 by sigma raised to 3 by 2, and sigma is your variance, root of your variance, and so the skewness will be s cube, which is equal to 1 by sigma raised to 3 by 2 integral of 0 to infinity t minus t bar, and t bar is your mean residence time, the whole cube E of t dt. So this is your skewness. So these three, the mean residence time, variance, and skewness are often called as moments of RTD or moments of residence time distribution. And in gate, there will be questions where you'll be given a set of data with regards to E of t, and you will be asked to calculate the mean residence time, your or the variance or the skewness, and you can just directly apply this formula in most of the cases and just find your answer, right? Okay. So another thing that you can use, let's say, as a sort of shortcut for this mean residence time. So let's say if you are given a residence time distribution like this, a sort of an isosceles triangle or something. So this starts as 0 and this is at t. So if you are asked to find what is the mean residence time t bar here, what you can search for is the geometry of the residence time curve. So here, if you divide this curve at this middle point, what you will have is both these sides will be having equal geometry or equal area. So what you can say is, you can say this halfway point is your mean residence time, and this is applicable only for equal geometry figures like this isosceles triangle, or if you have mean residence time like this. So the halfway point will usually be your mean residence time. In cases which are not identical, having identical geometry, you can use your formula, which is integral 0 to infinity t e of t dt, to find your mean residence time, and follow the same steps to find the variance and skewness, right? Fine. So one more thing we'll just look into before we go into the questions. So yeah, we were looking at residence time distribution for the pulse tracer, right? So let's say we have a pulse tracer residence time pulse tracer that is introduced in a CSTR. Then how will your residence time distribution look at the inlet of your or basically how will the pulse tracer look in a CSTR? So in a CSTR, so this is E and this is T. Yeah. So in a CSTR, this residence time distribution for a CSTR will be somewhat like this. Okay. This is your residence time, and the point at which it starts at time t equal to 0, this will be 1 by tau, and tau is your space time. Similarly, you can have RTD for PFR. So for PFR, it will be basically your delta Dirac function, or this straight curve, an impulse curve like this. And the time at which this function occurs is your tau for PFR, right? Now, if you have, let's say, CSTR and PFR in series, so let's say you have a PFR, then it is followed by a CSTR. Then your resonance time distribution will be like this. Okay. So this will be your tau PFR and this will be 1 by tau CSTR, right? And you can even have, CSTR and PFR in parallel. So, okay. So CSTR and PFR in parallel, it will be something like this. Okay. And you can have, a variety of, RTDs as well. You can have, let's say, yeah, something like this PFR with bypassing. So for PFR with bypassing, you'll have, something like this. So this small curve represents your bypassing basically. And, you can have another case, let us say, bypassing in CSTR with bypassing. So let us say this is your 1 by tau m or tau CSTR. The curve will be, stagnate at the initial point and then it will like, come like this. And this portion is your, you know, bypassing volume or space time. So yeah, you can have, variety of residence time distribution for, different situations and different reactors and so on. So yeah, this I hope this served as an introduction to just non-ideal reactors. We'll still have, a lot of other curves. I know a lot of other things to discuss with regards to non-ideal reactors. So today we looked into something called as an E curve or the resonance time distribution. We also have something called as an F curve. We have, all these curves for step inputs. So we'll look into all these things in the coming classes. So yeah, this is all for today. We'll start looking into some previous set problems. But before we move on, if is there any doubt with regards to this? If things are clear, we can move on. But in case if anyone has any doubt, just you can type or unmute and speak. Okay. So I'm guessing things are fine for as of now. And if that's okay, then we'll just move on to the problems part, I guess. Yeah. So just go through this question and let us see how we can solve this question in a couple of minutes. And yeah, most of the questions that will be, I mean, not most, all of the questions that we'll be discussing today are based on your E curve only, like based on the concepts that we learned so far. So just go through the question. So this is a question from GATE 2015 from Chemical Engineering, question number 55. The impulse response to a tracer pulse experiment for a flow reactor is given below. In the figure, C is the exit tracer concentration. The corresponding E or E theta curve or the normalized E curve is correctly represented by which of the following choices? Here theta is dimensionless. And the four options given are as here. So this is a question from non-ideal reactors and residence time distribution, and the reference from NPTEL can be found in module 1, lecture 53, RTD for various reactors part 2, Chemical Reaction Engineering 1, Homogeneous Reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question, they have given us an RTD for a particular situation. So this is our RTD given, and we can see that the RTD curve is basically an isosceles triangle. And we are asked to find which of the following options here represents the correct RTD choice. So the curve that is given for us is basically, C versus T curve or concentration versus time curve. And we need to find the, most matching RTD curve or E versus T curve. So the concept that we'll be using here is basically, area under the E curve. And area under the E curve is equal to 1 integral of E of t dt. So what we can do here is find the area of the four options that is given to us here, and if any of these area under the E curve is 1, then that will be our answer. So what we'll do is we'll find the area under these curves. So the first one, the area under the triangle is basically, for triangle, area is half base or half into base into height. So for the first case, the area here is half into 4 into, this is 0.25, 0.25. So this is basically 1 by 2. So this is not equal to 1. So A cannot be our option. And we do the same for the remaining three options. So the area under the second curve will be half into 2 into 2, and that is 2. And the third one is half into 4 into 0.5, and this is 1. And just for surety, we'll also calculate the final area, which is half into 4 into 5, and that is 10. So area under E curve for option C is 1. So that is our required residence time distribution, or E versus T curve or the E curve. So the right answer here is option C. Right. So this is just a straightforward application of the area under the curve concept that we just looked into a few minutes ago. So whichever E curve gives the area as 1, that is your correct E curve for the particular situation. And not just for this particular situation, for any situation or any reactor, the area under your E curve should always be 1. So that is what we tried to find here. We found the areas of the different RTD curves that were given to us, and the area under the curve, which was 1, is our correct option, and here that option is option C. Fine. Okay. Let's move on to another question. So this is a question from GATE 2016 from Chemical Engineering, question number 50. A CSTR has a long inlet pipe and a tracer is injected at the entrance of the pipe. The E curve is obtained at the exit of the CSTR as shown in the figure below. Assuming the plug flow in the inlet pipe, the ratio rounded off to second decimal place of the volume of the pipe to that of the CSTR is dash. This is a question from residence time distribution, and the reference NPTEL lectures can be found in module 1, lecture 58, direct use of RTD to predict conversion, part 1, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here the RTD curve that is given to us is of this form. So this is basically the RTD that is given, and the other information that is given is that there is an inlet pipe which is connected to a CSTR, and the data that is given, just a second, பார்சலா என்ன எது ஃப்ளிப்கார்ட் தானே மொபைல் கிடைக்கல எனக்கு இன்னும் அது 7:30 தான் கிடைக்கும் நான் வேணா அவள் மெசேஜ் அவளுக்கு அனுப்பிச்சா பொறுமை என்னன்னு கேளு okay, sorry about that. So yeah, so the given here is that we have a long inlet pipe which is which acts as a PFR, and this is then connected to a CSTR. Okay, and the RTD representing this system is given in this form. So for RTD that is given here is basically the RTD of a system which is consists of PFR followed by a CSTR. So that means this point here represents tau PFR or the space time of PFR, and this point represents tau CSTR or the space time of CSTR. So we will use this data to find the ratio of the volume of the pipe to that of CSTR. So from the graph, we can have the two datas here, that is tau PFR, which is 5, and this 0.05 is 1 by tau CSTR. So 1 by tau CSTR is equal to 0.05, or basically tau of the pipe is 5 and tau of the CSTR reactor will be 1 by 0.05, or you can write it as 1 by tau of the CSTR as 0.05. So here they have asked us to find the ratio of the space times of the or the volumes of the pipe by the volume of the CSTR. So the ratio of the space time will be equal to the ratio of the volumes of the pipe and volume of the CSTR. So this ratio will be equal to tau pipe, which is 5, divided by tau CSTR, or that is equal to into 1 by CSTR, and that is into 0.05. So this ratio will be 5 into 0.05, and that is 0.25. So the ratio of the volume of the pipe to that of CSTR will be 0.25. Okay. So again, this is basically a straightforward question using this RTD curve. So they have given us a system which basically means a system starting from PFR followed by a CSTR, and we have the information that this point here at 5 will be the spacetime of the PFR, and this point on the y-axis will be the inverse of or 1 by spacetime of CSTR. So using these two data from the residence time curve, we can find the ratio of the volume of the pipe to that of CSTR directly. Fine. Okay. Um, Fine. Let's look into one more question. Okay. So this is a question from GATE 2017 from Chemical Engineering, question number 46. The C curve measured during a pulse tracer experiment is shown below. In the figure, C of T is the concentration of the tracer measured at the reactor exit in mole per liter at time T seconds. The mean residence time in the reactor rounded off to one decimal place is dash seconds. So this is a question from residence time distribution from non-ideal reactors in chemical reaction engineering, and the reference NPTEL series can be found in module 1, lecture 53, RTD for various reactors part 2, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question we have been given a C versus T plot for a particular pulse tracer experiment, and we need to find the mean residence time T bar, and the T bar can be found as integral 0 to T into E of T dt, 0 to infinity. So here let us divide this curve into two. So redrawing this curve, we had this was our RTD for 0, 1, 2, 3. So up to time 3 seconds. This was the concentration versus time curve. So what we can do is we can divide this concentration versus time curve into three parts. So this will be part 1, this is part 2, and this is part 3. So our mean residence time is given by integral 0 to infinity T into E of T dt. So just a second. Okay, sorry about that. So now the thing is, we have the C versus T curve. So what we need to know that E of T will be, C by integral 0 to infinity C of T dt. So from this question, the area, so this is one. So we need to find the E curve first so that we can apply this formula here. So here, this the value of E can be, C of T divided by area under the C curve. So area under the C curve will be 1 by 2 into base into height, which is 2 into 1, and that is equal to 1. So what this exactly means is E of T, just a second. என்ன மயிறு, ச்சே. Sorry about that. Had to answer the door basically. So yeah. So okay. So now what this essentially means is E of T will be equal to C of T by 1, and that is C of T. Or in other words, E curve will be pretty much the same as the C curve because the area under the curve is 1. So our E curve will also be like this. So this will be our E curve. And here also what we'll do is, as we intended before, we will split this E curve into 3. This is part 1, this is part 2, and this will be part 3. Okay. So the mean residence time T bar is equal to integral 0 to infinity T E of T dt will become, integral T E of T dt for part 1 plus integral for part 2 plus the same integral for part 3. Right. Now one more thing we need to note here is that the E of T dt, or the integral that integral of E of T dt is basically the area under the curve. Okay, sorry about that. That is a mistake. Yeah. Okay. So yeah. So basically, the residence time T bar will be a sum of the integral T E of T dt for part 1 plus integral T of T E of T dt part 2 plus integral T E of T dt part 3. So now what we have to do is we have to find E of T for part 1, part 2 and part 3. Okay. So from the figure for part 1, it is basically a straight line like this from 0 to 1 in the x-axis and 0 to 1 in the y-axis. And we can represent this line in the form of y equal to mx, right? So here y is e of t and x is t. So e will be equal to m into t. Here the slope is basically 1. So this curve or this line can be represented as e of t, which is equal to t. So let us say this is for part 1. Now similarly, we can do the same for part 2. Now in part 2, this is from 1 to 2, and the x-axis is t and y-axis is e, that goes from 0 to 1. So this equation can also be represented as y equal to mx plus c. So here y is e and m again is the slope, and that is minus 1. So minus x plus c. C is the intercept, and this will intercept the y-axis at 2. So E of t for part 2 will basically be 2 minus t. Now, sorry. Now let us move on to part 3. So for part 1 we had E of t as t. Then for part 2 we had E of t as 2 minus t. Now part 3, E of t is basically 0 because it just coincides with the x-axis t, and E of t for this line will be 0. So E of t for part 3 will be 0. So now getting back to our formula, mean residence time t bar is equal to integral of 0 to infinity t e of t dt, and we had divided this into part 1, part 2 and part 3. So this will be integral 0 to 1 t e of t dt for part where e of t is the e of t from part 1. Then this is added to integral 1 to 2 t of t into e of t dt for part 2 plus integral 2 to 3 t e of t dt for part 3. Now e of t for part 3 is basically 0, so the third term will get cancelled. So now what we can do is we can substitute the e of t's from part 1 and part 2 into this equation. So mean residence time t bar will become integral 0 to 1 t into e of t for part 1 is t and e of t for part 2 is 2 minus t. So we'll substitute that here. This will be 0 to 1 integral 0 to 1 t into t dt plus integral 1 to 2 t into 2 minus t dt. So this will be our final integral equation. So now all we have to do is integrate the equation and apply limits. So t bar is 0 to 1 t square dt plus integral 1 to 2 2t minus t square dt. So this will be integral t cube, this will be t cube by 3 from 0 to 1 plus 2 t square by 2 minus t cube by 3 from 2 to 1. So now if we apply the limits, this will be 1 by 3 minus 0 plus 2 into t square, that is 2 square by 2 minus 2 into 1 square by 2 minus t cube by 3, applying from 2 to 1, that will be 2 cube by 3 minus 1 cube by 3. And if we do this mathematical operation here, we'll get the final residence time t bar is equal to 1 second. So the required mean residence distribution time here will be 1 second. A shortcut for this can be, because this residence time distribution has an identical geometry like this, we can say that the point at which both the part 1 and part 2 becomes identical, which is the halfway point of this triangle, that will be our mean residence time t bar. And from the graph, it is at this point, and that means the mean residence time at this point will be 1 second. So this is like a shortcut method to find the mean residence time for residence time distribution that has identical geometries. Fine. So what we did here basically is we tried to find the mean residence time using your standard method, which is by using the formula, and the final few seconds we just mentioned, regarding the identical geometry. So here in this question, we had an identical geometry, and because of that we could find the mean residence time, by just cutting through the halfway point. But if you wanted to do it in the normal standard way using our formula, this is our formula, which is, t bar is equal to integral t into e of t dt, and we have to find e of t for these different lines that we have in the e curve. So that is what we did here. So we found the, equations for E of t for part 1, part 2 and part 3 in this question, and then, finally just integrated everything and summed everything, and finally we just applied the formula directly and we got the final residence time as, or mean residence time as 1 second. Okay, this is slightly an elaborate process, I know, but yeah, this is like, one of the standard methods to do it. So what you can do is, if since you have, since you can divide your residence time distribution into three different parts, what you can do is you just divide the, residence time into three different parts, find equations for E of t. Here the thing that we used was y equal to mx plus c, concept, because all the residence time curves were basically straight lines. So we used y equal to mx plus c here, and we found, the terms for E of t for, different lines, and then finally just integrated and added them together to get the mean residence time. Fine. Is this clear to everyone? Are the questions and concepts that we discussed here, were somewhat clear to everyone, I hope? Okay. Okay. Good. Yeah, I mean, these things are like just some of the basics when it comes to non-ideal reactors. I mean, there are a lot more things mm, that's there in the non-ideal reactors. But anyways, this is some of the basics with regards to the residence time distribution or the E curve for non-ideal reactors. And these three questions that you just saw are like some of the standard questions that you can expect in GATE exams by using the concept of the E curve or the residence time distribution. All right, fine. So we'll stop here for now, and yeah, we'll start with the remaining part of the residence time distribution and the step inputs and F curves for non-ideal reactors from next class, and we'll see how it goes from there. We'll try to solve some problems as well using this E curve and F curve concepts in the next class. All right. So yeah, that's it for today. Um, Thank you for joining, and I hope to see you guys next Monday.